In these slides, we're going to look at matrix multiplication. This is where things start to get a little bit complicated, but also a little bit more fun. We're going to look at, well, how do we do matrix multiplication? That would be a good place to start, right? How does matrix multiplication differ from the regular old multiplication you're used to with multiplication of numbers and functions and things like that? And we will revisit the identity matrix and learn more things that are cool about it. So before we do matrix multiplication in its full-blown fashion, we're going to take a little mini problem. And we're going to take a row and a column. Note that they have the same number of entries. Like each of these would have 5 entries or maybe 3 entries or whatever, but they have the same number of entries. You can tell that by the indexing. These are just 2 little vectors. One's a row vector, one's a column vector. We're going to form something called the row-column product, which means just do the dot product of the row and the column. So R1 times C1 plus R2 times C2, all the way down the line to the product of the last entries, all of them added up. So remember this, row-column product is just take a row and take a column, pretend they're both vectors, do their dot product. So here's an example. We want the row-column product of R and C. So we'll take the -2 and the leading 1, multiply. We'll take the second entries, 1 and 2, multiply. Take the third entries, 1 and 3, multiply. Take the last entries, multiply. And that comes out to be 3. So we take a row, we take a column, we do the dot product, we do the row-column product, we get a single number back. Hold on to that. So you have 2 matrices. You really want to multiply them together. Are you allowed to? If I hand you 2 numbers, you can always multiply them. If I hand you 2 functions, you can always multiply them. If I hand you 2 variables, you can always multiply them. If I hand you 2 matrices, you may not be able to multiply them. There is a test, and it's based on the size of the matrices. So we have matrices A and B. These don't have to be square, so A is M by R, M rows, R columns. B needs to be R by N, so R rows and N columns. Those 2 numbers, the R's, the number of columns of A, the number of rows of B, they have to be the same number. And if they are, then you can multiply the 2 matrices together. The number of columns of the first must be the number of rows of the second. If you can do the matrix multiplication, then it's those outer numbers that tell you the size of the result, M and N. Okay, that's pretty abstract. Let's look at some examples here. So we've got 2 square matrices, 3 by 3. The green numbers are the ones you check. The second number in the sizing of A, the first number in the sizing of B. That's the number of columns of A, the number of rows of B. Are those numbers the same? Yes, they are. So we could do the product AB. And then the size of that would come from the outer numbers, the 3 and the 3. So the product AB is permissible, and it would be a 3 by 3 matrix. So let's keep A as a 3 by 3 matrix, but change B to a 2 by 2. Can we do this product? Well, check those middle numbers, the 3 and the 2. They are not the same. This product cannot happen. So let's let A be a 3 by 2 and let B be a 2 by 2. Number of columns of A is 2. Number of rows of B is 2. Those inner numbers match. You're good to go. You could do this multiplication if you knew how. And the result would be the outer numbers, 3 by 2. 3 by 2 times 2 by 3? Yes, you can. The sizing result is 3 by 3, those outer black numbers. 3 by 2 times 3 by 3? Nope, not going to happen. Columns of A, rows of B do not match. So now we know how to check if we can multiply 2 matrices together. Next, we can learn how to do the matrix multiplication, and this is where we're going to go back to the row-column product idea. Let's take 2 matrices. You check their sizes. Okay, we're good to go. We can form the matrix. We're going to go through each entry that we're going to form in this new product matrix. We know what size it's going to be, right? So we know how many entries to look for. For each entry, we're going to say, hey, where does this entry sit? Okay, second row, first column. That means we're going to go take the second row from the first matrix in the product and the first column from the second matrix and do that row-column product to put the result in that spot. Here's what I mean by that. Over here on the left, we have two 3x3 matrices. We can do that product, and we know ahead of time the result is going to be a 3x3 matrix. So here is an empty 3x3 matrix waiting for numbers to be put in. How do we get the numbers? Well, let's take this spot right here. That is in row 1, column 1. That means we're going to go back over to the left and grab row 1, and we're going to grab column 1, and we're going to do the row-column product. So 1 times -1 plus 2 times 1 plus 3 times 6. And when you run those numbers, you're going to get 19. And so that's the number that goes in that new spot. On the right-hand side, say sitting in the spot where the 5 is, well, where is that? That's in the 3rd row but 2nd column. So back over here, 3rd row, and then 2nd column, do the row-column product. -2 times 3, 1 times 1, 2 times 5, add it all up, you're going to get 5. So at this point, I recommend that you pause this and figure out what numbers need to go in the remaining spots of this matrix on the right, and then when you're done, come back and start this up again and see whether you got that result. If you didn't, try again or find my mistake. And if you did, good work. Carry on. So this time we're just going to take those two matrices and flip them around. So on the previous page we did A times B. Here we're going to do B times A. They're both 3x3s. The product will be a 3x3. We're good. Go ahead and check all the results. Do a whole bunch of row column products. You're going to end up doing 9 of them, right? And see that these are the resulting entries. And then notice something interesting. We had two matrices A and B, same matrices. On this page is B times A. On the previous page, it was A times B. Are those two results the same? They are not. Okay, so AB and BA are totally different. And this is interesting because this does not happen with multiplication of numbers, variables, or functions. Right? In those cases, order of multiplication does not matter. With matrix multiplication, order most definitely matters. Here's a multiplication of matrices that are not the same size. Now it looks strange, but you can do it. Remember, to add or subtract, the two matrices would have to be the same size. To multiply, you check that the number of columns of the first is the same as the number of rows of the second. In other words, look at the descriptors. The first one is 2 by 3. The second one is 3 by 2. The middle numbers, the 3 and the 3, if you were to put those together, 2 by 3, 3 by 2, the middle numbers, 3, match. We're good to go. The outer numbers, 2 and 2, tell us the size of the resulting matrix. So this 2 by 3 matrix times a 3 by 2 matrix will produce a 2 by 2 matrix. We produce it the same way. This red 8, where is that sitting? Well, that red 8 is sitting in row 1, column 2. And that means we went to the left, we took row 1, we took column 2, we did the row-column product. 1 times 2, 2 times 3, 3 times 0. Add them up, 8. And then the 0 is produced similarly. Go ahead and see if you can finish those last entries. I will wait. I won't whistle, though. You can pause. That's the result. Okay, something for you to think about. That last slide, we had a 2 by 3 by a 3 by 2. We made that product happen, it worked, and the size was 2 by 2. If we switched it around and did BA, would that work? And if it could work, what would the size of the result be? So again, going from 2 by 3 times 3 by 2 produces a 2 by 2. If we change the order, we'd be doing a 3 by 2 times a 2 by 3. Can we do it? And what would be the size? Think about it. Let me know if you have questions. So here's the important thing to remember. If you can do matrix multiplication in both orders, they may not be the same. And sometimes you could do AB, but you couldn't do BA because of the sizes of the matrices. So you just always have to be really careful about can you do the product, and don't jump to conclusions about what happens if you change the order. Order matters. The other thing that can happen is you can take two matrices, multiply them together, and get a matrix that's totally full of zeros, even if the originals were not totally full of zeros. So this is another break to that rule that, hey, if you took two things and multiplied them and you got 0, one of the originals had to be 0. That is not true here either, just like it wasn't true for dot products. Last thing, let's take a look at the identity matrix one more time. We learned how to identify it in Part A of Unit 1, where it's a diagonal matrix with ones down the diagonal, zeros everywhere else. Why is that an important matrix? Well, let's think about the number 1, from kindergarten or whenever the first time you ever learned the number 1 was. What are some of the special things it does? Well, it behaves as the multiplicative identity. That means you multiply 1 by another number, and you just get that other number back. 1 times A equals A times 1 equals A for any A that you want. There is a matrix that does this in matrix multiplication, and it's called the identity matrix, and it looks the way we've already designed it. And it just so happens that if you take an identity matrix and another matrix which is of the right size, that you can do the multiplication, that multiplication, I times A, or A times I, will both produce the same thing. It will return A itself, and that is the job of the identity matrix. So if you look through the details of this, you can confirm that it works. So just pause this and confirm that 1001 times ABCD in either order will actually produce ABCD right back again. That is how the identity matrix does its thing. And there's the same deal for a 3x3 matrix, and then you could write down a similar pattern for 4x4 and so on. And that is all the fun you can have with matrix multiplication.